Hello, it's Mr. Doro. Today's lesson we're going to be learning about empirical and molecular formulas, which is also called formula stoichiometry. And we're going to learn how to identify empirical and molecular formulas when you're given the information you need. There are a couple definitions that you need to know. Molecular formula, you already know what it is. It is where you have the formula showing the number and kinds of atoms that are in a compound. For example, C4H10 is a molecular formula. It has 4 carbons and 10 hydrogens. Here's another one, C8H20, 8 carbons and 20 hydrogens all bonded together there. An empirical formula, though, is related to these, but it's the lowest whole number ratio or the simplest ratio of the elements in a compound. So for example, for this C4H10 right here, that could reduce down to simpler forms, and so that would reduce down to C2H5 because both of those are divisible by 2, both of those subscripts. And so this would be the empirical formula right here for this molecular formula. And if you look at this one, 4 would go into each one of these, and it would reduce down also to the same empirical formula. So these both have the same empirical formula, C2H5. Although these are not the same compound, they have the same ratio of carbons to hydrogens. Here are some simplified steps for finding empirical formulas. I'd like you to write these down. They're really taken down as small as I can so that you didn't have to write so much. But step 1 is you'll be given percentages, and you want to change those percentages to grams. Then you want to divide those grams for each element by the molar mass for that element from the periodic table. And then you divide each answer by the smallest number that you got from step 2, and use the whole numbers as subscripts, and if needed, multiply each subscript by 2 to get the whole number, to get whole numbers. This step won't show up very often, and we'll talk about it as we get to it. So here's a typical problem that you'll have to find the empirical formula. This one is giving you 3 different elements that are in there, a carbon, a hydrogen, and oxygen, and it gives you the percentages by mass. So we're going to do step 1, assume that you have a 100-gram sample to make each of the percentages equal to grams. And so we're going to do that by saying I like to label them as carbon, hydrogen, and oxygen so that I don't get them all mixed up. They're easy to get mixed up. So since carbon was 40.00%, we're going to say it is 40.00 grams. We just changed that percentage to grams. Hydrogen is going to be 6.72 grams. And the oxygen, 53.28 grams. If they were 100%, that's how many grams each one would be. Then our next step is to divide each mass by the molar mass for that element to change it to moles. So for carbon, it is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. And the oxygen is 16.00 grams per mole. And so you divide these and you'll end up with the moles for each one. And so I've divided each one of those. In the carbon, I end up with 3.331 moles, hydrogen 6.65 moles, and oxygen 3.330 moles. My next step, I have to determine which one had the smallest amount of moles and divide each of the moles by that number. Carbon had the 3.331, 6.65, and 3.330. This is my smallest one right down here, so I'm going to divide each one by 3.330, and I may not end up with an exact whole number, but I should come up pretty close. And the answers I got were 1.000, 2.00, which actually was 1.99699, so on and so forth, but in 3 sig figs it winds up to be 2.00, and this obviously is going to be 1.00. I just didn't have room for the sig figs. Now these answers that you end up getting here are the subscripts because these are mole ratios. 1 mole of this to every 2 moles of this and 1 mole of that. And so they won't always end up this pretty. Sometimes they'll end up as 0.96 or 2.05 or 2.1. They usually should be within a tenth of, and you can round. Many times it's because we round our molar masses and to 2 places after the decimal. So when I write this one is all whole numbers, so everything's okay. And so my empirical formula is C, and there's only one C because right here and then so I don't write a 1 on there. And then the next one is H, but there are two H's because of this part right here, two H's. And then finally I got my O, and there's only one O because of this ratio. This is a 1 to 2 to 1 ratio, and this is my empirical formula right here, CH2O. Now if I end up with those ratios and one of them is around 1.5 or something like that, I can't, that's too far away from the whole number to round it, so I would have to multiply each of those by a number, and in order to make them all whole numbers, by the smallest number that will make them whole numbers, and usually if you double it, that'll usually end up working. Once we determine the empirical formula, we can easily find the molecular formula if we remember that the empirical formula is the simplest form of the molecular formula. So the molecular formula has to be some kind of multiple of the empirical formula. And so all you got to do is determine the mass of the empirical formula that you just found, find the mass of the whole thing from the periodic table, and then see how many times that mass will go into the molecular mass, and then however many times it is, that's the factor that you multiply each subscript by. Alright, so if you notice this problem, this is actually the same problem that we had before. 40% carbon, 6.72% hydrogen, 53.28% oxygen. So we already know the empirical formula from our problem before, but here is the added part. It has a molecular mass of 120.12 AMUs. Now, that is for the molecular formula, and so we can determine the molecular formula from this. If you remember what we had before for the empirical formula, it was CH2O. So what we have to do is we have to find out the mass of this from the periodic table. We look up carbon, and that's 12.01, plus hydrogen, which is 1.01 times 2, because there's two of them, plus oxygen, which is 16.00. Now when we add those all up, we end up getting 30.03 AMUs. That is the same as the molar mass, the same number as the molar mass, but a different unit because it's only for one molecule, so it's atomic mass units. And then we have the molecular mass for the molecular formula right here is 120.12 AMUs. So what we need to do is find out how many times this goes into this one right here, and that would be the multiple that we have to multiply each one of these subscripts by in order to get the molecular formula. So we're going to set that up, and we're going to say 120.12 AMUs divided by 30.03 AMUs. I'll be good and write my units on there, and I end up with a factor of 4. That factor should be a whole number, and if it wasn't, then you probably switch these two around. You want to put the bigger number on top. This means that I need 4 sets of this empirical formula, and so I need to multiply each subscript here by the 4, and so my molecular formula ends up being C4H, you got it, 8, and then O4. That would be my molecular formula for this. And here's one more example. This one only has 2 elements in it, phosphorus and oxygen. So I'm going to go through each of the steps right here. We're going to start out, I'm going to label them phosphorus over here and oxygen. That way I don't get them mixed up when I get my numbers at the end. It's so easy to get those mixed up. So I start out with 43.6 grams of this and 56.4 grams of that. Divide each by their molar mass from the periodic table. 30.97 here and 16.00 here for oxygen, and I get a number. And the answers I got were 1.41 and 3.53. And so I find the lowest of those two numbers, and I divide each one of them by that. 1.41, 1.41. This one I can do in my head. It's going to be 1. And this one ends up being 2.50. That's my mole ratios, 1p to every 2.50 O's. And so this one, I can't round this one right off. Now, a tendency for a lot of students is they stop right here and they say, oh, 1.41, well, that's around 1.5, and this is around 3.5. You have to make sure you're dividing by the smallest number, and then you get your answers here for the actual mole ratios. So this is 1 to 2.5. Now, I can't have P 2.5. I can't have a subscript as a decimal, and this is too far away, the 2.5, to round it. So this is where I got to do that step 5. I got to multiply each one of these by a number to get whole numbers. So I'm going to do these times 2, because that gives me 5.00, and this gives times 2 here, don't forget to multiply them both by 2, gives me 2.00. So my empirical formula ends up being P2O5. Now I can't reduce that down any further, so that is my EF, empirical formula, right there. So that's the empirical formula, and then it says find the molecular formula when the molecular mass is 283.88. So now I got to find the molecular mass of P2O5, which I would find as 30.97 times 2, plus the 16.00 times 5, which I get to be 141.94, and so then that is my empirical formula mass. I look up here, here is my molecular formula mass, so I need to find out how many times this goes into that, and so I take that bigger number, that 283.88, divided by this, and I get 2. Which means that there are 2 of these empirical formulas in the molecular formula, which means my answer would be P4O10. That is my molecular formula. I want to put molec formula right there. Now I've got 2 problems for you to do. This is the first one right here. You're going to have to pause it. Carbon 52.13%, hydrogen 13.15%, and oxygen 34.72%, and it gives you a molecular mass of 184.32. Go back and look at the problems. If you're having trouble, go through each of the steps. Pause it right now, and then go on to the next one. This last one only has 2 elements, again, like that second problem we did. 36.86% nitrogen, 63.14% oxygen. So find the empirical formula first, and then the molecular formula by using that molecular mass of 228.06 AMU. Alright, this stuff is not too bad. You just gotta keep trucking and go through it. Have a good night. Bye-bye.